Grounding electrode conductors and grounded conductors are distinct components in an electrical system. A grounded conductor is intentionally connected to ground, while a grounding electrode conductor, or GEC, connects the non-current carrying metal parts of a system to ground. A critical requirement is that the grounding electrode conductor must be bonded to the grounded conductor at the service entrance. This bonding ensures that the grounding electrode conductor maintains the same potential as the grounded conductor. By maintaining the same potential, any fault current that flows through the grounding electrode conductor can be safely discharged to ground, minimizing the risk of electrical shock or damage. The National Electrical Code, or NEC, dictates the sizing requirements for the grounding electrode conductor. The appropriate size depends on two primary factors. Firstly, the size of the service conductors, and secondly, the type of grounding electrode system employed. It is important to consult the NEC tables and guidelines to determine the correct size of the grounding electrode conductor for a specific installation. Proper installation of the grounding electrode conductor is crucial for its effectiveness. Installation methods must comply with the standards set by the authority having jurisdiction, or OJ. This typically involves housing the grounding electrode conductor in a raceway or another approved enclosure to provide physical protection and ensure its long-term reliability. The National Electrical Code provides specific guidelines for sizing grounding electrode conductors. For example, an NEC Table 250.66 is commonly used to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The table provides a straightforward way to correlate conductor sizes and ensure adequate grounding capacity. It is essential to refer to the latest edition of the NEC, as these tables may be updated. The grounding electrode system can consist of various elements, each with specific requirements. Common types include metal underground water pipes, concrete encased electrodes also known as UFRs, ground rings, and rod or pipe electrodes. Each of these grounding electrodes has specific installation and sizing requirements detailed in the NEC. For instance, if a metal underground water pipe is used as a grounding electrode, it must be supplemented by an additional electrode, such as a rod or pipe electrode. This is because the water pipe connection may not be reliable over time due to potential replacements with non-metallic pipes. Concrete encased electrodes must meet certain specifications regarding their size and placement within the concrete foundation. Ground rings must be buried at a specific depth and encircle the building or structure. Rod and pipe electrodes must be driven to a certain depth and may require multiple electrodes to achieve the desired resistance to ground. The NEC also specifies the materials and construction requirements for grounding electrode conductors. Typically, copper or aluminum conductors are used. Copper conductors must be protected against corrosion, especially when in direct contact with earth or concrete. Aluminum conductors must not be used in direct contact with concrete or in locations where they are subject to corrosive conditions. The grounding electrode conductor must be continuous and without splices or joints, except where permitted by the NEC. If splices are necessary, they must be made using irreversible compression connectors or exothermic welding to ensure a permanent and reliable connection. In addition to sizing and installation, the NEC addresses the bonding of various metal parts within the electrical system to the grounding electrode system. This bonding is essential to create an equipotential plane and minimize voltage differences that can pose a shock hazard. Metal water pipes, gas pipes, metal building frames, and other conductive elements must be bonded to the grounding electrode system. The bonding conductors must be sized according to NEC Table 250.102 and installed in a manner that provides a low impedance path for fault current. The purpose of bonding is to ensure that all metal parts are at or near the same electrical potential. This reduces the risk of electric shock if a person comes into contact with two different metal parts that are at different potentials. Bonding also helps to facilitate the operation of overcurrent protective devices, such as circuit breakers and fuses, by providing a low impedance path for fault current flow back to the source. The NEC also addresses the grounding requirements for separately derived systems, such as generators and transformers. These systems must have their own grounding electrode system, which is separate from the building's grounding electrode system. The grounding electrode conductor for a separately derived system must be sized according to the derived phase conductors and connected to a grounding electrode that meets the requirements of the NEC. Separately derived systems require special attention to grounding because they create a new source of power within the building. Without proper grounding, these systems can create dangerous voltage differences and increase the risk of electrical shock. Grounding electrode conductors must be protected from physical damage. If the grounding electrode conductor is exposed to physical damage, it must be installed in a raceway or other approved enclosure. The raceway or enclosure must be securely fastened to the building or structure and provide adequate protection against impact, abrasion, and other forms of damage. The type of raceway or enclosure used depends on the specific installation conditions and the requirements of the AHJ. Common types of raceways include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and rigid non-metallic conduit. The NEC also addresses the use of ground clamps for connecting the grounding electrode conductor to the grounding electrode. Ground clamps must be listed for the purpose and made of a material that is compatible with the grounding electrode and the grounding electrode conductor. The ground clamp must be installed in a manner that provides a secure and reliable connection. It is important to ensure that the ground clamp is properly tightened and that the grounding electrode and grounding electrode conductor are free from corrosion and other contaminants. Regular inspection and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. The grounding electrode system should be inspected periodically for signs of corrosion, damage, or loose connections. Any problems that are identified should be corrected promptly. Regular maintenance can help to prevent electrical hazards and ensure the safety of the electrical system. In summary, understanding the requirements for grounding electrode conductors is essential for electrical safety. The NEC provides detailed guidelines for sizing, installing, and maintaining grounding electrode conductors. Compliance with these guidelines is crucial to protect people and property from electrical hazards. Consulting with a qualified electrical contractor is recommended to ensure that the grounding electrode system is properly designed and installed. Always refer to the latest edition of the National Electrical Code and local regulations for the most up-to-date requirements. The grounding system is a critical safety component of any electrical installation, and its proper function is essential for preventing electrical shocks and ensuring the safe operation of electrical equipment.